Students, and welcome to today's session. So today we'll be completing the heat and thermodynamics part with the completion of the last section of heat transfer, which will be radiation. In the last lecture we have discussed about applications of heat conduction, including some integration examples, etc. Now we come to the other mode of heat transfer, which is called radiation. So let's begin. Okay, so we have been studying about heat transfer in the last couple of lectures. As we know that there are three modes of heat transfer: conduction, convection, and radiation. Conduction is something that we've already studied about. Convection is something we will not really be studying as part of our syllabus, because convection is the primary mode of heat transfer. In fluids, and it occurs through a phenomena which is called convection currents. Now, convection currents are somewhat unpredictable and complex. They are not described by simple equations, but rather they have to be described by some kind of simulation modeling, which goes outside the scope of our 10+2 level discussion. So therefore, they cannot be described by any simple formulae or equations. But rather they are studied by a process of simulation. From experimental data. That happens at the engineering level. So this is not in our 10+2 syllabus. Okay. Now let's come to the third mode of heat transfer, which is radiation, which we'll be talking about primarily today. So radiation is the heat transfer through emission or absorption of electromagnetic waves. So this is quite different from both conduction and convection, because it does not involve kinetic energy of a material medium, or it does not involve vibrational or translational kinetic energy of the molecules of actual physical materials, but rather it involves the exchange of photons or packets of electromagnetic waves or electromagnetic energy between matter and its surrounding. So the important thing is radiation does not involve the kinetic energy of the molecules of a material medium, but rather involves exchange of energy by emission or absorption of photons. So as you know, photons are quanta or packets of electromagnetic energy. Okay. Between a body and its surroundings. So as you're already familiar with certain part of atomic structure, you know that all atoms and indeed molecules also, they consist of energy levels in which the electrons exist. These are the energy levels for electrons in atoms. Then anytime an electron makes a transition from a lower energy state to a high energy state, in the process it will emit a photon. So if it makes a transition like this, it results in emission of a photon. It results in absorption of a photon because it has to absorb energy to go from the lower to a higher energy state. So anytime an electron makes a transition from lower to higher energy state, it has to absorb a photon. Okay. So this is an example of absorption of a photon for an electron to transition from lower state to higher state. Okay. Of course, the opposite of this can also happen. An electron in a higher energy state can transition to a lower energy state, and in the process it might emit a photon. I mean, it will emit a photon if it makes a transition. So in such a process, there will be an emission of a photon. Okay, from atomic structure, you already know that energy of a photon is given by the formula hc by lambda. But that's not going to be important for us over here. What is more important, this is a process where an electron will emit a photon when it transitions from higher to lower energy state. Okay. So this is the primary mechanism by which matter is constantly emitting / absorbing photons from its surface. And that process of exchange of photons from its surface, or exchange of photons between the surface of a body or the surface of a material and the surrounding material, or the surrounding environment, that process of continuous exchange of photons is what we call radiation. So since radiation does not require a material medium for exchange of heat between two bodies or two materials, it is the only form of heat transfer that happens through the vacuum of space. So for example, the solar radiation, which is incident on the Earth's surface, is the mechanism by which heat is transferred from the sun's surface to the Earth's surface. So radiation is something that is abundant in a huge amount in everyday life around us. Okay, by radiation, we don't mean only the type of gamma radiation which happens in nuclear reactions, which can be extremely lethal. Okay, we mean radiation of everything. Like when you look at any material or any body, the color that you're seeing of it is because of the radiation of photons of certain specific wavelengths that is happening from its surface. So radiation occurs across the entire electromagnetic spectrum. Okay. Typically, radiation occurs in the infrared, ultraviolet, and visible light region abundantly. X-rays, microwaves, etc. are also examples of radiations, part of the electromagnetic spectrum.
Sir, cosmic rays.
Yes, cosmic rays are examples of radiation. Yes. Okay. So, as I was saying, one very important point is that radiation is a form of heat transfer.
So this is continuation of thermodynamics only, no?
Yeah, I mean, this is the last part of heat transfer, right?
Okay.
So there are three modes of heat transfer: conduction, convection, and
radiation.
right. And as I told you, like convection, we will just know about it theoretically, that it is the type of heat transfer that happens in a fluid because of the setup of convection currents. Little bit idea you have about what is convection currents. That
Yes,
convection currents is the actual flow of fluid molecules from region of higher temperature to region of lower temperature and vice versa, because of the temperature difference creating a difference in kinetic energy of the liquid molecules. Okay. However, that exact path in which the convection current flows and the rate at which heat transfers and all that is much more complex and unpredictable compared to something like conduction, which we studied through a simple equation of heat transfer or simple equation of heat.
So conduction,
okay.
so conduction is predictable, whereas convection is unpredictable.
Yes, I mean convection is also predictable, but the exact mathematical relationship between the amount of so that is not something that is so easy to describe by equations and all that. Okay, so for example, the rate of convection will also depend on the shape and size of the container in which the fluid is kept. Okay, if it is a cylindrical container versus a cuboidal container, the effect that the corner walls will have, because as you set up the convection currents, there will be collisions with the corner walls with respect to the molecules in motion, etc. So all that makes it very much more complex. So there are simulation models which are studied in a particular subject called computational fluid dynamics.
Sir.
Yeah.
Sir, can you send the module for thermodynamics, heat and thermodynamics? We haven't received the module for it.
Okay, I will send it on the Blue House group again then. Okay. Yeah. It's module number 3 of physics. So in case you have not managed to collect it or you've not got it before.
Okay.
Okay. Yeah, Shikhar, I will scroll up. So we'll come back to this point. Okay. Or actually, let me finish writing down this point, then you can write down everything together. So radiation is a form of heat transfer which does not involve the kinetic energy of the molecules of a medium. Okay. And therefore, propagates through vacuum of space. Okay. So it becomes the only mode of heat transfer through space. Okay. So example, heat transfer from a star to planets. That heat transfer occurs only through radiation.
So what is written after therefore?
Just a moment. Yeah, what are you asking, beta?
So after therefore, what you have written?
Just a moment. Radiation is a form of heat transfer which does not involve kinetic energy of molecules of a medium, and therefore propagates through vacuum of space. It propagates through the vacuum of space.
Yes, sir.
So will we have questions like find the energy by hc by lambda or h nu?
You will have that thing later when we discuss about photon theory of light in a section called modern physics. Okay, if you look at the last section of H.C. Verma part 2 now, you will see that there is photon theory of light, then Bohr's model of atom. So that section cumulatively is called modern physics. So in that we will be discussing about energy of photon, relation with wavelength, okay, and properties of photon and all that. In this section we'll be studying something else which is called Stefan's law of radiation and Newton's law of cooling. So that actually will not involve the relationship
Sir,
between
Vien's black
wavelength
body
and energy.
radiation. So black body radiation.
Yes, black body radiation. That's correct. Okay. So Stefan's law basically relates black body radiation.
Okay, sir.
So I'm coming to that. It's like quite an easy portion, radiation. We'll finish the discussion today itself about it. So today we'll be in a position to finish the syllabus of heat and thermodynamics. Maybe next lecture we'll keep aside some time for some doubts and questions, but then we'll be ready to start the next portion of this physics syllabus.
Sir, so modern physics is somewhat like what we did in what we did in chemistry,
Atomic
like
structure.
in
हाँ,
atomic
atomic
structure.
Yes, yes, yes. Structure of atom में lot of elements that you studied about are to do with modern physics.
Okay.
दोनों सर सेम
Especially-
चैप्टर है बेसिकली इट्स जस्ट लाइक केमिस्ट्री में है और 11th में और 12th में फिजिक्स
Yeah, exactly. Like Bohr's model of atom, you know, the quantization of energy levels, angular momentum quantization, MVR is equal to NH by 2 pi. The energy of photon is Hc by lambda. These are all things that we'll be understanding in more detail in modern physics. Okay, but along with that, we'll study a few more things like photoelectric effect. Okay, then we'll study about X-rays in detail. We'll study about nuclear physics in quite a bit of detail. You must have heard of the very famous equation E is equal to mc square, no?
यस सर
Einstein's
Yes, sir.
mass energy relation. So again, that
Yes.
is something we will study about in nuclear physics. And the
सर
concept
we
of
have
rest
its
mass.
derivation nuclear physics
No,
में
unfortunately, it is one of the postulates, na? So we don't have a derivation for that, but we will understand its implication. Okay, with
derivation
respect to nuclear
it's
physics.
a very beautiful derivation sir if you were to understand
Yeah, I mean, it can be explained on the basis of relativistic equations like dynamic mass and so. So we will talk
relativistic
about
mass
that.
sir relativistic mass का equation के साथ they have started a derivation
Yeah,
I kind of
you can.
understood it थोड़ा
You can show the derivation to a certain extent, or you can show the logic of it from that relativistic mass concept.
yeah
Okay, so anyway, so far these things are clear, right?
Yes, sir.
Okay, so now we come to Stefan's law of radiation. So as part of this, we will study about black body radiation also, but we will study about radiation from any general kind of body also. Need not be a perfect black body. So of course, to understand, I have to first explain what is a black body also. So don't worry, we'll come to that. So Stefan's law of radiation is basically something like this, that, see, we just discussed that radiation occurs, okay, in the form of emission and absorption of photons from atoms as they are undergoing transitions. The electrons inside the atoms are undergoing transition from lower energy state to higher energy state and vice versa. Now, the rate at which these transitions occur and when which atom will make a transition this is completely random because it is driven by something called the quantum mechanics of the atom, and quantum mechanics is a probabilistic kind of process, So there is no way of predicting that a given atom at a particular time will be absorbing or it will be emitting, or after how much time it will be undergoing a transition. But when we look at a whole cluster of atoms together on the surface of a body which is exposed to the outside environment or something, we can make a prediction about the cumulative rate at which they will be absorbing or emitting heat. We cannot say that, okay, we cannot pinpoint that a particular atom at which point of time it will emit, at which point of time it will absorb. But when we are looking at the whole surface as a whole, we can make an empirical average that, okay, at a given instant of time, what is the rate at which it will be absorbing energy through photons, and what is the rate at which it will be emitting energy through photons. So that experimental analysis and the data correlation of that was done with by Stefan Boltzmann, and that is what is denoted by the Stefan Boltzmann or the Stefan's law of radiation. So Stefan's law of radiation basically says like this, that if we have the surface of a body, okay, radiation is a surface phenomena. It's a phenomena which occurs at the surface of a body with respect to its environment. So if a surface exists at temperature T, okay, in kelvins, then the rate at which the surface is emitting energy by radiation, rate of emission of energy by electromagnetic radiation will depend on surface temperature, okay, surface area. The larger the area, the more it will emit, or
The
vice
more is the
versa.
intensity of radiation.
Yeah, yes, the larger the surface area, the more it will emit, the larger rate at which it will emit. And the third is it will also depend on the material of the surface. Okay.
So material is actually the primary factor.
Yeah, I mean, these are factors. I'm not saying one is more important than the other. Okay. So the maximum rate of radiation is by what is called a black body. A black body is a material which is a perfect emitter or the perfect absorber of heat. So I'm coming to that. Okay. So related to this now is a definition which is called the emissive power. A capital E. The emissive power, now the name is a little misleading because power is in watts, but emissive power is in watts per meter square. It is the rate of emission per unit time, or you can say it is the rate of energy emitted.
Sir, per unit time and per unit surface area also, no?
Yes, yes. Okay. So it is the rate of emission of energy per unit time per unit surface area. Okay. So therefore it is expressed in joules per second per meter square, or simply watts per meter square. So 1 watt is 1 joules per second. Okay. Yeah.
Sir, just like a black body possesses the property of maximum rate of radiation, it also possesses
Emission.
maximum rate of absorption also, right?
Yes, yes, yes. Black body is both the perfect emitter as well as the perfect absorber.
Yeah, yeah. So like for example, Vanta black, sir, 99.8% light it absorbs. Vanta black, the darkest substance ever made by humans.
Right. Lamp black is also something which has very high level of emissivity and absorptivity. So there is a parameter that we will learn called emissivity or absorptivity. They are one and the same thing. Okay, so a black body is something which theoretically has the value of emissivity equal to 1, which is the maximum possible. But most materials will have emissivity. I mean, all materials have emissivity less than 1. and very few specialized materials have emissivity in the region of 0.99 and above. Okay, so lamp black and all this comes in that category, right? So anyway, the first experimental fact that was part of the Stefan's law of radiation is that the emissive power that depends on temperature. How? It depends on absolute temperature to the power 4. Okay, and the constant of proportionality involves the material property which is called the emissivity. Okay, and the universal constant for radiation, which is called the Stefan Boltzmann constant of radiation, multiplied by T to the power 4. So I'll just explain these terms. Just note down up to here first.
Sir? Hello?
Sir, what is sigma?
Yeah, but you were asking me something? Yes.
Yeah. Sir, just like sir, we were going to learn Wien's law of black body radiation. So we also learn about Planck's law of Planck's theory of black body radiation alongside it, because it was derived
We
from
will
the.
study about the Planck's constant and how it is related to energy of photon.
Okay.
Okay, that will come in photon theory of light and photoelectric effect. Okay. Whereas this Wien's displacement law we will be talking about in part of radiation only. Okay.
Radiation. Yeah.
Yeah. Okay, so now in this
Sir,
equation,
here sigma is what? Sigma and E.
yeah, I'll
Can you
explain.
repeat
So
again?
these are both constants. Okay.
Okay.
So here sigma is a universal constant called Stefan Boltzmann constant of radiation.
Okay.
Now sigma is the constant which is universal. That means it does not depend on the material of the surface or the surrounding or anything else. Now, like universal gas constant, it's same for all gases. Like that, it's a universal constant, and it has an experimentally determined value of 5.67 into 10 raised power minus 8 watts per meter square Kelvin to the power 4. Okay, now if you understand the unit of sigma, you'll realize that the small e is a dimensionless quantity because capital T is in watts per meter square and T to the power 4 is in Kelvin to the power 4. Okay, so I'll just write this a little more properly. So this is Kelvin to the power 4. Okay. So you don't need to memorize the value, it will be given to you in the question paper, but it's a universal constant. So most of the time in questions, they will ask you to take the approximate value of this to be 6 into 10 raised power minus 8 watts per meter square Kelvin to the power 4. Whereas small e, it is a material property, okay, of the surface, and it is called emissivity. So emissivity is first of all unitless or dimensionless, and emissivity is less than 1, between 0 and 1 for all known materials.
It cannot be equal to or equal to 1 or 0.
Yeah, equal to 1 is for a theoretical material called the black body, which is the perfect emitter of heat.
Okay. So even Vanta black is nowhere equal to 1.
No, it is less than 1. Even Van der Black or even your lamp black, etc. So E is equal to 1 for a black body. Now a perfect black body is a hypothetical material.
Sir, what about a black hole, sir?
What about a black body? I'll explain. So a
No,
perfect
black hole, sir, black hole.
black hole, yeah. I mean, theoretically, it is argued that
that
it can have an emissivity almost equal to 1.
Yeah.
Because of the very high gravitational field. Okay, because of this super dense mass.
Infinite density.
Yeah, infinite density. So perfect black body is the hypothetical material
Okay.
which is the perfect
Sir, so even black hole
emitter.
is not equal E equal to 1.
See, the thing is now, like, it is equal to 1 up to a certain error. Like any measurement in physics is subjected to error, no?
Okay, yeah.
You understand? No? So there is an experimental measurement error involved. So it's like the closest to 1 with a very, very small margin of error.
Yes, sir.
If you check out in a proper book of cosmology or something, I think you will find the error of lesser than 10 raised to minus 30 order of magnitude.
Yeah. Minus 30,
Something like
minus
that.
40, 42. Yeah.
Sir,
So for practical purpose, you can say E is equal to 1 for a black hole. But then, you know, a black hole is a very extreme situation. Like closer home, if we are doing some, you know, proper thermodynamic experiment with bodies on the surface of the Earth, there is nothing that comes reasonably close to E equal to 1 in real materials which are accessible. You know? The maximum, I think, is 99.2 or 90. I mean, in percentage, 99.2. So in value of E, it will be 0.992 or
Yes.
0.993, something like that.
Yeah. Understood, sir. Yeah.
Okay. So this is about emissive power. Okay, and in through that we have understood the property of emissivity. Now very soon we will see something very interesting, that anything which is a good emitter is naturally a good absorber also, and therefore a perfect black body not only has emissivity equal to unity or 1, but it also has absorptivity equal to 1. Okay, but there's a logic behind that and we'll understand that. Okay. So
So it would
now
be inverse of emissivity, right?
it's like inverse in the sense that it's the opposite process, it's absorption.
No, if we were to
So
talk
what?
mathematically, sir, if we were to talk.
No, it's not inverse. I'll explain.
No,
Okay.
yeah.
So according to Stefan's law, see what is happening. If the surface is at a temperature T, okay, but also it is in a surrounding, and the surrounding temperature is T naught, again in kelvins. Okay. Now you know it's not possible to have absolute zero. You know, it's theoretically impossible to have absolute zero.
Yes.
So a surrounding temperature of T naught kelvins will mean that also the body is, the surface is continuously absorbing photons. Because remember that process of electronic transition, whether the electrons transition from lower to higher state absorbing photons or from higher to lower state emitting photons, that is probabilistic. So irrespective of the fact that the temperature of the surface might be more than the temperature of the surrounding, still some atoms will go in that direction where they are gaining energy by absorbing photons from the surrounding instead of losing energy by emitting photons. Okay, so that process of emission and absorption keeps taking place simultaneously. So any surface continuously, okay, absorbs as well as emits radiation simultaneously. So that's why it has not only an emissive power, but it also has an absorptive power.
Sir, can you explain
both
this
are
one more
equal.
time?
Come again, people. Can I explain the?
Yeah, sir, can you explain how it continuously absorbs as well as emits radiation simultaneously?
Yeah. So see, basically, what's happening? The emission and absorption. What is the primary reason why it's happening? Is the ability of the atoms to undergo transition from low energy state to high energy state.
Yes,
So
sir.
basically, you know, if you're in a if the body is in a surrounding temperature of T naught, it is in a radiation field now of the surrounding.
Yes, sir.
So in that radiation field, there are photons present. So there is always a probability that some of those photons will be absorbed and the atoms will undergo transition from lower state to higher state. Just like there is a probability that atoms will lose energy and emit photons, like that there is a probability that atoms will gain energy by absorbing photons also. Because after all, the surface is present in an external radiation field.
Okay, sir, got it.
Understood the point now? So unless we are in that impossible situation where T naught is zero, impossible because that's again a theoretical state where molecular activity ceases. Okay. So whatever is in the surrounding of the body, I mean, even if the environment is vacuum, but there must be some other body like a star or something nearby which is emitting radiation. So it is present in a radiation field. So it will always have this process of continuously absorbing radiation also, and at the same time continuously emitting its own radiation, because some of its atoms will also go from higher energy state to low energy state. So it's like the two processes are continuously trying to balance each other, absorption and radiation.
Sir,
You can understood the point now?
Yes,
so
sir, got it.
every kind
Yeah,
of
so it
point,
continuously, yeah, beta, come again.
sir, so every point will have different kinds of energy. Since
Yes.
there's simultaneous absorption and radiation.
Yes, it's sort of trying to
emission.
come to an equilibrium. By emitting and absorbing, it's trying to come to an equilibrium. Of course, the perfect equilibrium will be there when the surface temperature is equal to the surrounding temperature. Okay, so the surface has something called absorptive power. Just like it has emissive power, it has something called absorptive power, which is generally denoted by the
Absorptivity.
symbol capital A. So this is the energy absorbed per unit area per unit time. By per unit surface area per unit time. So this absorptive power is proportional to temperature of the surrounding to the power flow, where T naught is in kelvins. Okay. And it is given by the formula absorptivity into Stefan Boltzmann constant into T naught raised power 4.
Sir, so it depends on the surrounding temperature, no?
Yes,
Completely.
it depends on the surrounding temperature. Exactly. Okay. Now E is absorptivity, which is a material property. Now, just like emissivity, E is between 0 and 1 for all known materials. Okay. And we will understand that E is equal to 1 for a black body. Now, this statement we'll understand in just a moment when we realize that it's not just that E is equal to 1 for a black body, but actually emissivity is equal to absorptivity for any material. So if a particular material has emissivity equal to 0.7, its absorptivity will also be equal to 0.7. So this might seem like a very curious statement initially, but it will make sense. Just we'll.
Sir, can you elaborate?
Yeah. So
Sir, because we
emissivity,
earlier stated that any surface absorbs as well as emits simultaneously.
and
That's
not only
why
that,
both their values should be equal.
yeah, why they should be equal? Because when the situation reaches thermal equilibrium, the rate of absorption must be equal to the rate of emission. So for that to happen, the only possibility is that the emissivity must be equal to absorptivity.
Yes.
Okay. So we will understand the proof of this statement in just a moment. Okay. So for any given material, the value of emissivity is equal to the value of absorptivity. Okay, so finish writing up to here, no? So now let's understand.
sir.
Okay, finish up.
Done.
Yes, done. No? Okay, so now first of all, let's understand a situation where if the surface temperature is equal to the surrounding temperature, is identical to the surrounding temperature, okay, then what should happen? Then the given body is in thermal equilibrium with its surrounding. Okay.
Sir, this kind of thermal equilibrium, there will be emission or absorption?
See, both will be taking place simultaneously. So the net rate of heat exchange will become zero. Okay. So the net rate of heat gain or loss, whichever be the case, should be zero. Okay. So what is happening is absorption and emission will simultaneously keep taking place continuously in such a way that they completely balance each other. So whatever heat per unit time the body is gaining by absorption, the same amount of heat per unit time it will lose by emission, and in the process the net rate of heat transfer will become zero. Okay, so while the net rate of heat gain and loss is zero, but keep in mind that emission and absorption are continuously taking place simultaneously. But in such a way that they balance each other. So such a way that the net rate of exchange, that should become zero. Okay. So how is that possible? Let's understand. So if we have a surface of surface area S and temperature T, what is the rate of heat emission? So we can see dQ by dt emission, that should be equal to the emissive power multiplied by surface area, because emissive power was heat radiated per unit time per unit area.
Yes.
So it should be E sigma into surface area into T raised power 4. Okay, and if it is in a surrounding of temperature T naught, so what is the rate at which it is absorbing? The rate of absorption, that should be equal to similarly E into sigma into surface area into T naught raised power 4. It should be absorptive power into surface area. So it should be absorptivity into sigma into the same surface area but into surrounding temperature to the power 4. Now see what this statement is saying here. This statement is saying that when T is equal to T naught, okay, dQ by dt net should be zero. So that means the rate of absorption should be equal to the rate of emission provided T is equal to T naught. You understood the statement now? So now
Sir,
when
the
you
dQ by dt you wrote net should be equal to zero. No?
That is the net should be zero. The net rate of heat loss should be zero. Okay, it's like, you know, you are spending money and you are earning money, but at the same time, if the net rate of wealth gain or wealth loss is 0, that means the rate at which you are spending is exactly balanced by the rate at which you are earning. You understood the point?
Yes.
That's the best way to understand this. Or let's say you have a tank in which you are filling water from one end, but also there's a tap from which water is leaking out. So if the rate at which you're filling is exactly balanced by the rate at which it's leaking out, the overall volume of water will remain constant.
Yes, sir.
No, so it's something like that.
Okay.
So the condition now becomes this, that from these two you can see, but this equation is satisfied when T is equal to T naught. This is for T equal to B equal to T naught. So that means E sigma S into T raised by 4 should be equal to A sigma S into T naught raised by 4 for T equal to T naught. Okay, so that means the emissivity must be equal to the absorptivity. This is the proof that the emissivity of any material is equal to the absorptivity. Right?
Sir, but in this case, we took that the surface temperature is like equal to the surrounding now. So is this still like valid if it's not equal?
Yeah, sorry, people, I missed that. What was the question you asked?
So in this case, you've taken that T is equal to T naught,
Huh.
and then we got E is equal to A. But what
Yeah.
if T wasn't equal to T naught, would the results still be the same?
Nee, so see, understand one thing, na? Emissivity and absorptivity, they are the material property. Na? So if we want to check the relationship between the emissivity and the absorptivity of a given material, we can check it in the condition that the surrounding temperature is equal to the surface temperature, right? Like the value of emissivity will not change if I change the temperature of the body. Na?
Yes, sir.
Whatever is the emissivity will remain the same whether the temperature of the surface is 0 degrees C or 100 degrees C or 50 degrees C, and same for absorptivity. It will not depend on the surrounding temperature. Okay, but if I'm getting a particular relationship when the surrounding temperature is equal to the temperature of the surface, then that relationship between E and A will hold for any temperature, na? Because E and A are material properties, they're not dependent on temperature.
Yes,
Is the
sir.
point clear?
Yes, sir.
Okay, so whether the equilibrium is occurring at room
So it is
temperature or it's occurring at 50 degrees C or at 0 degrees C, the fact that whenever the surface temperature is equal to the surrounding temperature, the rate of emission must be equal to the rate of absorption. So that itself means that the emissivity must have a numerical value which is exactly equal to the absorptivity. That
So what is
material
S
property
over
is actually,
here?
S is the surface area.
Surface area.
S is the surface area.
Sir, sir, that is only E will be only equal to A in thermal equilibrium, no?
No, that's what I'm explaining better. See, E and A, they are material properties. Their value does not depend on the temperature.
Okay.
You understanding? No? So whether I've created the
Yes.
equilibrium at 0 degrees C or 40 degrees C, but as long as there is equilibrium, the two rates must be equal. So the two rates can only be equal when E is equal to A. If I had such a material whose value of E is greater than its value of A, then in equilibrium, it should be emitting more than it's absorbing. But that doesn't make logical sense. Now, equilibrium means that rate of emission has to balance the rate of absorption.
So can the rate of heat emission and absorption be 0?
No, it cannot be, no, because 0 Kelvin does not exist in practice, right? Remember,
Okay.
T and T naught are temperature in Kelvin. No? So other than absolute zero, which is a theoretical state where all molecular activity ceases, okay, it cannot exist. No?
Yes, sir.
Okay. Okay, so this statement is clear na, that emissivity is equal to absorptivity. So now through this now we can understand a better definition of emissivity and absorptivity. So first of all, we have understood that emissivity is equal to absorptivity for any material. Okay, and all real materials have emissivity less than 1 or absorptivity less than 1. Okay, that's the first thing. Okay, now emissivity is equal to absorptivity equal to 1 for a black body. Okay, so a way to understand emissivity for any material is equal to the emissive power of that material divided by the emissive power of a black body. Okay, at a common temperature. Okay, because emissive power of the material will be equal to E sigma into T raised power 4, where E is less than 1, whereas emissive power of a black body will be equal to sigma into T raised power 4, because E is equal to 1 for a black body. Okay, and likewise, absorptivity for a material is equal to absorptive power for that material as a ratio with respect to absorptive power for a black body at a common surrounding temperature. Okay, because absorptive power for the material will be A sigma into T naught raised power 4, where A is less than 1, whereas absorptive power of the black body will be equal to sigma into T naught raised power 4, because A is equal to 1 for the perfect black body.
Sir, so E of material is directly equal to the E, no?
Come again?
Sir,
E is is directly equal to A for the material. That's correct.
hello, sir.
Yeah,
Sir,
yeah. Tell me.
sir, I'm saying why are divided?
But I can't hear you properly.
But sir, why are we dividing by the E of black body or A of black body?
Because that is how we can measure the emissivity of a body. No? It is a comparison. See, what is emissivity basically? Emissivity is that material property that tells you that how well that body will emit in comparison to the perfect black body, which has emissivity equal to 1. Or what is absorptivity? It will tell you how well that material will absorb compared to the perfect black body. So you can see, if you divide these two things, this divided by this, you will get how much? You will get E, na? Understood the point, na? So if I say emissivity of a material is 0.5, that means it will have 50% of emissive power compared to a black body at the same temperature. So per unit time, per unit area, it will be emitting only 50% of what the perfect black body is emitting.
Sir, can you repeat? There was a network error.
Okay. See, if you just divide these two, na, this and this, you can understand that the ratio is E, na? So what is the meaning of that ratio? It tells you that if I have a material whose emissivity is equal to 0.5, that means that material will only emit 50% of what a black body will emit at the same temperature, per unit area. Is it clear now?
Okay, in comparison with.
Yes, so it is a comparison with respect to a perfect black body. Now, just like, for example, refractive index. Now, refractive index is a comparison of the speed of light with respect to the speed in a given medium. No?
Okay.
Speed of light in vacuum with respect to the, no, so like that, this is a comparison.
Sir,
Yes.
why are we using emissivity in the formula of emissivity?
No, we are using emissivity in the formula of emissive power, beta.
Yes, but
Capital
that
E is emissive power. Okay. Emissive power is power emitted per unit area. Okay. Whereas emissivity is a material property. It is dimensionless.
yes, sir.
That's true.
But then we are calculating E of material equals that ratio.
It is the
So
emissive
that's
power
not a
of that
formula, that's
material.
just a ratio.
Yeah. It's the emissive power of that material, which is now given by this formula, divided by the emissive power of a black body if the black body is kept at the same temperature as the material is kept. Understood,
Okay.
no? So the emissivity of that material becomes a comparison between that material's emissive power with respect to a black body's emissive power, provided the two are kept at the same temperature.
Yes. Okay, got it.
Okay, and
So it's
like
just
same goes for
coincidentally.
absorptive power.
So it's just coincidentally in the E of capital E of materials formula, because we are just using both of them to find E, right, as a ratio.
Yeah, so small e is giving us that ratio only, is giving us the comparison between the ability of that body to emit with respect to a black body to emit, which is a perfect radiation.
Yes, I understood. Thank you.
Okay. Okay. So now with all this background, we will also understand the net rate of heat loss or heat gain if we are not in a situation of thermal equilibrium. When there is no equilibrium, so suppose if the body's surface temperature is greater than the surrounding temperature. Okay, so what will happen? The radiation will result in a net heat loss from the surface, from the body's surface. Why this will happen? Because the net rate of emission or the rate of emission will become greater than the rate of absorption. Okay, so from that we can understand that the net rate of heat loss, okay, which we can write as minus dq by dt net. The minus sign is just showing us that it's a rate of heat loss. That should be equal to the rate at which the body is emitting minus the rate at which it is absorbing. Okay, is giving off more heat than it's absorbing, and that's why it's losing heat. So the net rate at which it's losing heat is the rate at which it's emitting minus the rate at which it is absorbing. Okay, so this minus dq by dt net, it will become emissivity into sigma into surface area into temperature to the power 4, whereas the net rate of absorption, or in fact we can write an intermediate step first. We can write this as the rate of emission will be emissive power multiplied by surface area, and the rate of absorption will be absorptive power multiplied by surface area. And next we will substitute emissive power and absorptive power in terms of Stefan's law. Okay, so if this is a surface which is of area S and temperature capital T, and it's in a surrounding of temperature T naught, okay, where T is greater than T naught, so it will be losing heat. You'll observe that with time the body will be cooling down because its rate of emission dominates over its rate of absorption. So the rate of emission, which is emissive power multiplied by surface area, this becomes E sigma into surface area into T raised by 4, and this becomes absorptive power into sigma into same surface area but into surrounding temperature to the power 4. Okay, now we know that E is equal to A for any material. So that means we can write the net rate of heat loss as E into sigma into S into T to the power 4 minus T naught to the power.
So,
Yes.
sir, since
Yes,
the heat
tell-
is lost as a result of it, we are taking a negative of dq by dt.
Yes, because the negative sign shows us that there is a heat loss. Okay, negative sign indicates the body is losing heat because its own temperatures of the surface is greater than the surrounding. So the direction of heat flow should be from higher temperature to lower temperature. The net, the net transfer of heat should happen from higher temperature to lower temperature.
Sir, in this case, the object is not in thermal equilibrium with the surrounding, but still A will be equal to E, na?
Because E and A are material properties. Na? They are not dependent on what the temperature is.
Yes, sir.
You understand? Na? So the fact that we already know that emissivity is equal to absorptivity, that is a universal fact for that material. It does not vary with temperature.
Yes, sir.
Okay, so let's look at an example of this. So we have, let's say, a solid metallic cube. Okay, which is at some comparatively higher temperature. So this is a solid metallic cube of dimension L by L by L, where the side length is 2 meters. Okay, its surface has a temperature of 127 degrees C at the given instant. Okay. And the surrounding temperature is 27 degrees C, normal room temperature. Okay. Also given that Stefan's universal constant, we can take the approximate value of 6 into 10 raised power minus 8 watts per meter square Kelvin to the power 4. And emissivity of the metal is equal to 0.6. So we want to find the emissive power and absorptive power in watts per meter square each. And we want to find the net rate of heat loss in watts. So this is a direct numerical substitution. Just try it out. It will just give you an idea of how to use the equation that we've been talking about, the Stefan-Boltzmann equation of radiation. Okay, so the first thing you have to be careful about in these calculations is units. So remember that you will substitute T naught and T in Kelvin, okay, in your equations. So the first part, emissive power will be emissivity into sigma into temperature of the surface to the power 4. So emissivity was 0.6, okay. Sigma we have taken as 6 into 10 raised per minus 8. Now temperature of the surface, we will have to keep it as 400 Kelvin, okay, because 127 degrees C is equal to 400 Kelvin. So this will take as a temperature of the surface. So this is becoming 0.6 into 6 into 4 to the power 4 into 10 raised per minus 8 into 100 to the power 4. So these two will automatically balance each other. So that is 16 square or 0.6 into 6 into 256. Okay, this is in watts per meter square. Okay. So 921.6 watts per meter square is the emissive power it is the energy emitted per unit time per unit surface area. Okay. Now likewise you can find the absorptive power. It will be A sigma into temperature of the surrounding to the power 4. So A is equal to E is equal to 0.6, but surrounding temperature will be 300 Kelvin. Because 27 degrees C is 300 Kelvin. So absorptive power will become 0.6 into 6 into 10 raised to power minus 8 into now similarly 300 to the power 4. So you do this calculation, you see this will come out to be 81 into 3.6 or 291.6 watts per meter square. So this will be the absorptive power. The energy absorbed per unit time per unit surface area.
So for net rate of heat gain, it's the same formula with the positive sign, right?
Net rate of heat loss
And
होगा ना बेटा यहाँ पे.
yeah,
Yeah. See, gain will happen when T is less than T.
हाँ
Okay,
तो
but if
A
T is greater than
minus
T
ये
naught, so if it is that situation where the temperature of the surface is less than the temperature of the surrounding, then absorption will be dominating over emission. Na? So we'll have plus dq by dt net, that will become rate of absorption minus rate of emission.
yes, sir.
Right? Okay. But this is of course a case where T is greater than T naught, so there's a net rate of heat loss.
Yeah, so there will be a minus sign over here.
Yeah, there'll be a minus sign, and don't forget that these are emissive power and absorptive power, whereas net rate of heat loss is in watts, not in watts per meter square. So you have to also take care of what is the surface area. So for that, the dimensions of the cube are given to you, no?
Yes, sir.
So make use of that also, So make use of this also. Okay. So let's understand the second part. So net rate of heat loss. This will be minus dq by dt net. So that is the rate of emission minus the rate of absorption. Okay. And by doing all those calculations, you can see it is equal to E into sigma into surface area into T to the power 4 minus T naught raised power 4. So basically it is this surface area into emissive power minus absorptive power. Now the surface area here will be 6 times L square, 6 faces of the cube.
Yes, sir.
Right.
6 L square.
Yes, sir.
L was 2 meters, so it is 24 meters square. Okay. So it will be 24 multiplied by 921.6 minus 291.6. So this will be in watts.
151.
So this is the rate at which it is losing heat. Okay. Yeah. So this will become
15120. Sorry.
okay. Okay, so this is an example of a direct type of question for application of Stefan Boltzmann law. Okay, now likewise, if the temperature of the surrounding is greater than the temperature of the surface, then a body will tend to gain heat by radiation. Okay. And we will have plus dq by dt net will become the rate of absorption minus the rate of emission. So that will tell us that plus dq by dt net will become E sigma into surface area into temperature of the surrounding to the power 4 minus temperature of the surface to the power 4. Okay, so this is the
But this was logical, right? Hello. सर अभी तक नहीं आया क्या?
नहीं
नहीं आया।
नो
सर का कुछ नेट का प्रॉब्लम है।
हाँ हाँ पता है।
अरे पीयूष थोड़ा
Yeah, sorry students, I had some network connectivity issue. I think it is all resolved now. Let's check. Yeah, so hope the previous question was clear to all of you, how we calculated the net rate of heat loss. And after that, we are discussing that if the temperature of the surrounding is greater than the temperature of the body, then there is a net rate of heat gain like this. Okay. So with regard to this, let's look at a quick question. Now see, in JEE level, you will not have direct questions like that. You will have more complex questions, okay, which will involve not just the direct application of Stephen's law of radiation, but also some additional concept along with that. So let's look at an example of that type of a question. So in this, we will see that there's going to be a system where there will be a combination of radiation and absorption. Radiation and conduction. So let's say we have got this kind of a system. So we've got a metallic cylinder. Like this, and this is all insulation. But the two faces of the metallic cylinder, as you can see, they are open. So this is an insulated box. This is insulation. But this one here is a solid metallic cylinder. Now the metal has thermal conductivity given to us of 200 watts per meter Kelvin. Okay. And both the surfaces are open. Open surface. Open surface. Okay. Now inside this, there is a heat source which maintains constant temperature of T1 equal to 500 Kelvin. Okay. Whereas the surrounding temperature is 300 Kelvin. This is the atmospheric temperature. Whereas this open phase, this has a steady state temperature of 400 Kelvin. So first of all, given that the metal has an emissivity of 0.5, calculate the length of the cylinder. Because at steady state, the temperature of the surrounding is, the temperature of this surface is 400 Kelvin. Okay. And secondly, if the cylinder has a cross-sectional area of 20 centimeters square, then find the rate at which the heat source generates heat. The heat source is continuously generating heat. That's how it's maintaining the temperature of the inner chamber constant at 500 degrees C. Okay. So think little carefully in this question and tell me what all phenomena of heat transfer are happening in this. Can you tell me how many phenomena of heat transfer you can see that are happening in which the metal cylinder is involved?
Sir, conduction and radiation.
Yes, very good. There are two phenomena that is happening. There is a heat current that is going across the length of the conductor from this end at T1 and to this end at T2. So there is conduction happening. And then this end is exposed to an atmospheric temperature which is less than its steady state temperature. So there is a net rate of heat loss that is happening through this via radiation. So there is conduction happening through the rod's length, across the rod's length through it. And there is also radiation happening at the open surface. There is a net rate of heat loss happening at the open surface. Now, if the open surface is at a steady state temperature, that means its temperature is remaining constant. That means the net rate at which it is receiving heat from the left side by conduction must be equal to the net rate at which that surface is losing heat because of radiation.
Yes, sir.
So by balancing the two, you will get the condition for steady state, and from that you will get the unknown quantities which are required. Okay, so just try out this question. So this is the type of question you will expect at JEE level for radiation, because otherwise it's like direct substitution, so it's like too easy. Also in this question, take the value of sigma, Stefan's constant, as the approximate value as 6 into 10 raised power minus 8, just to make the calculation easier. Watts per meter square Kelvin to the power 4. Okay. So now that you understood that both the things are happening, conduction and radiation, and the two are balancing, so just write the equation for that. Yeah, Piyush, I'm just going through your messages. Yeah, about the ultraviolet catastrophe and Wien's displacement law.
Yeah.
Okay. Yes, we will be discussing about this also in the next lecture. Okay.
So there were two scientists, sir, which predicted the ultraviolet catastrophe. Wien's displacement law proved it accurately.
Yes. But you know, the proof of it accurately comes from the quantum mechanical explanation.
Yeah, sir, it was the onset. So this took place during the onset of the development of the quantum mechanics.
Yeah, it was one of the first, major successes of quantum mechanics, because the
after which Sir Planck understood and then formulated his black body radiation.
Yeah, radiation concept also. Because up till that point, people had proposed quantum mechanics, but it was not really widely accepted. But then there was that problem of ultraviolet catastrophe, which could not be. It was called catastrophe because the way the
yeah, sir, it's very peculiar and very funny, sir. Yeah, so it's very peculiar and funny, sir. Actually.
Right. It could not be explained by the classical model of heat.
Yes, sir. Yeah.
That's why it was called
catastrophe. It required a new approach, which was proved accurately by Wien's displacement law.
Correct. So that was one of the successes, and then later, of course, photoelectric effect, right, in which Einstein also played a major role. So that also, you can say, established the quantum nature of light.
Yes, sir.
In the question, what is T2?
Sorry, in the equation, what is?
What is T2 in the question?
Yeah, T2 is the temperature of this open surface. So, this temperature, this is the steady state temperature at which the open surface exists. Okay. So the open surface of the metallic cylinder, which is exposed to the outside environment, that is existing at a higher temperature than this because heat is coming from this side. So it's trying to lose heat and come to equilibrium with 300 outside, but at the same time it's gaining heat from the other side, which is coming by conduction. So it reaches a different kind of situation. It reaches a steady state. Instead of reaching an equilibrium with the outside environment, it reaches a steady state where its temperature remains constant at 400 because the incoming heat is always balancing the rate at which it is losing heat by radiation.
Okay.
So that is what we have to now apply. That if that surface T2 is at steady state temperature, that means its temperature is not changing with respect to time, then the net rate at which it's receiving heat by conduction must be balanced by the net rate at which it is losing heat by radiation. So the interesting thing is, see, for the first partner, you will not require the area also. That is why the area of cross section is given only in the second part. You have to, in the first part, you have to calculate the length of the cylinder. So for that, you will require thermal conductivity, emissivity, temperatures, and all this. Sigma, of course, is given to you, but you will not even require the area of cross section. So that means that answer is independent of the area of cross section.
Yes, sir.
Anybody got the answer for the length? Yeah, I'm seeing 38 meters per. Okay, let me check the calculation. Okay, so what we are saying is that across this length, the rate at which the thermal current is coming, okay, delta Q by delta T by conduction, that should be equal to T1 minus T2 by thermal resistance, or Ka by L into T1 minus T2. And then the rate at which heat loss is happening, minus dQ by dt net rate of heat loss by radiation. So for that, we can see that this is at a temperature T2 and the surrounding is at a temperature T0. So this is equal to E sigma into surface area, which we can now write as A, into T to the power 4 minus T0 to the power 4. Now this time capital A is surface area, it is not absorptive power. So for thermal equilibrium, or rather for steady state, what is happening? This heat current should be equal to this net rate of heat loss. So Ka by L into T1 minus T2 should be equal to E sigma into same cross-sectional area into T2 to the power 4 minus
T0 to the power 4.
Okay, so that's why it's the answer is finally for L is independent of the area. So we can see that K was how much? 200. This temperature difference is 500 minus 400, so that's 100 divided by whatever length. So this should be equal to the emissivity was 0.5. Sigma is 6 into 10 raised power minus 8. Okay, into this factor which is 400 to the power 4 minus 300 to the power. This will give us the length. So 2 into 10 raised power 4 divided by L equal to 3 into 10 raised power minus 8 into 4 to the power 4 minus 3 to the power 4 to 100 to the power 2. Sorry, 100 to the power 4. This is going to be 256 minus 81 into 10 raised power minus 8 plus 8. So L will become 2 into 10 raised power 4 divided by 3 into, what is this now? 25 minus 8. So that's 17, correct? So this much in meters. Let's see how much that works out to be. Yes, so 38.09 meters. This is the answer that I'm getting. Just verify that.
Yes, sir.
Parth, your answer is correct. Yeah. Okay, so this is the more typical type of question at the JEE level, especially JEE Advanced level, where you have to correlate the concepts of radiation and conduction possibly happening in the same question. Okay. Now the second part. So this is the first part. We have found out the length. And the second part, the area of cross section is given to us. That is 20 centimeters square or whatever. Okay. So now we can see that the heat current, okay, or that equals to the net rate of heat loss also. That is how much in watts. Okay, we can find that out, and that is the rate at which the heat source will have to generate heat. So that will be equal to the rate of heat generation by the heat source. So that will be equal to this. So 200 into 20 into 10 raised power minus 4 into temperature difference of 100 divided by the length, which is 38. So this will be in joules per second or watts. So this will be the rate at which the heat source is generating heat. This will be equal to this value. Okay, so hope this is clear to all of you. Right, so with that, we are coming to conclusion of today's lecture. Now, next lecture, we will see something very interesting called Newton's law of cooling, which shows us that when you have a body at surface temperature T in a surrounding of temperature T naught, if T minus T naught is very small compared to the surrounding temperature. No, or we can say that the temperature of the body is equal to the surrounding plus delta T, where delta T is small compared to T naught. Okay, then the rate of cooling, that is the rate at which its temperature drops, is directly proportional to temperature difference. Now this might seem like a contradiction, because today we have seen the net rate of heat loss by Stefan's law actually depends on T to the power 4 minus T naught to the power 4. But on this only, when we apply this condition that delta T is very small compared to T naught, and when we apply binomial approximation, we can justify this. And remember, Newton's law of cooling is something that had come from observation experimentally far before Stefan's law of radiation had been explained. So this was an experimental fact under this condition that delta T is not very large compared to T naught. So that experimental fact was later justified by Stefan's law's application only, but by applying some approximation method for the mathematics for the condition that T is close to T naught. So for example, it will not apply in a situation where the temperature of the surface is 400 Kelvin and the surrounding is 300 Kelvin, because then the temperature difference 100 is not very small compared to the surrounding. It will apply more in a case where the temperature of the surface might be 310 Kelvins and the surrounding is 300 Kelvin. Or better still, the temperature of the surface is 305 Kelvins and the surrounding is 300 Kelvins. Okay, so that's the next thing we'll see immediately after this, and its connection with Stefan Boltzmann law and few numericals and all related to that. And then finally, we will see about the spectral emissive power. That is, we'll understand about how the emission that happens from black bodies or bodies similar to black bodies is distributed over the spectrum of wavelengths. Okay, particularly across the visible, UV and infrared, and how the dominant wavelengths vary with respect to temperature, or the Wien's displacement law, or what Piyush was referring to today earlier as the ultraviolet catastrophe. So that part for syllabus wise is very simple for us. It will be just one single formula, but it's a very interesting aspect of physics, which had given rise to a lot of interest in quantum mechanics very early on in the history of quantum mechanics. We're almost at the very beginning of quantum mechanics history. So anyhow, with that, we will wind up heat and thermodynamics in the next lecture, along with some questions and doubts. Okay, the theory part will not take more than about half an hour. So rest of the lecture next time will be for discussion of questions and doubts. Okay, that's it for today's session, people. Wish you all the best.
Sir, we'll do all module doubts next class.
Yeah, at least the doubts that you have covered by then we can discuss. Otherwise, subsequently we can keep some time for doubt solving also. Okay.
Okay. Thank you, sir. Bye, sir.
Thank you, sir. Bye, sir.
Bye, sir.
Thank you, sir.